Welcome to math class. Yeah, welcome to math class. Summer's over, bell is ringing. New adventures just beginning. Gonna learn and have some fun now.
Hi, everyone. Welcome back. Today, we're moving beyond single transformations and looking at composite transformations. We're going to be taking square root, cubic, and cube root functions and throwing everything at them at once, such as flips, stretches, and slides. Okay, before we get into composite transformations, let's take a quick refresher of what single transformations look like. For all four of these, we're going to be looking at specifically f of x equals the square root of x. The transformation g of x equals a times f of x. This is a vertical dilation. In other words, it will stretch or compress the graph vertically. In the next one, we have g of x equals f of b times x. This is a horizontal dilation or stretch compress. We are looking specifically at the b value. In the next one, we have g of x equals f of x minus c. It is a horizontal translation, shifting left or right. Keep in mind, whatever C is, it is doing exactly the opposite. So if it says minus C, we're actually moving to the right. And if it says plus C, we are moving to the left. The next one is g of x equals f of x plus d. This one is a vertical translation. It is shifting the graph up or down, exactly what it says in the equation. So if it says plus d, it'll go up. If it says minus d, it'll go down. Finally, we have if a is less than 0, then we have a reflection over the x-axis. And if b is ever less than 0, then it reflects over the y-axis. If you've ever looked at an equation like g of x equals -4 times the square root of 2x plus 3 plus 1 and felt a bit overwhelmed, don't worry. By the end of this video, you'll be able to graph that in your sleep by following one simple order of operations. This covers everything you need for TEKS 4C and 6A of Algebra 2. So let's dive right in. By the time you are done, you'll be able to take this equation and come up with the following conclusion. Now, before we actually get in and work on the graphs and work on writing the equations, let's go through a step-by-step guide of how we can decode composite transformations. So what is a composite transformation? It is when two or more transformations are performed on a function graph to produce a new function. The common parent functions we're going to look at are going to be f of x equals the square root of x, f of x equals x cubed, and f of x equals the cubed root of x. The last two here, we're going to call these the S curves. That's how they looked for us. There are three steps that we are going to do to work on identifying. The first step is to check for reflection. The supporting details to look for negative values multiplied outside or inside the radical or cubed quantity. So the key word on this one is look for the multiplier. Anything on the outside of the radical or the cube is a vertical reflection. Anything on the inside of the radical cube is a horizontal reflection. So you want to look for a negative again. Just make sure. Step 2 is to check for stretch and compression. Identify if there is a factor multiplied outside or inside the radical or cubed quantity. If it's outside, that's a vertical stretch or compression. So if we're multiplying the function, then it's affecting the output. If it's on the inside of the radical or cube, then it's a horizontal stretch or compression. Next, you'll check for translation. You're going to look for values added or subtracted outside or inside the radical or cubed quantity. If it's outside, then it's going to be a vertical translation. And if it's on the inside of the function, it will be a left or right horizontal translation. Okay, now let's map out what a composite transformation looks like. G of x equals a times f of bx minus c plus d. Okay, first, a tells us two things. First, it tells us that there's a reflection over the x-axis if a is less than 0. It will tell us it's a stretch if the absolute value of a is more than 1, and it will tell you if it's a compression if the absolute value of a is more than 0 but less than 1. It is a reflection over the y-axis if b is less than 0. It will be a horizontal stretch if the absolute value of b is more than 0 but less than 1. In other words, it will pull the function outwards. It'll be a horizontal compression if the absolute value of b is greater than 1. In other words, it squeezes inwards. Next, we have c. It is a horizontal shift left if c is greater than 0. What you want to look for is plus c. It'll be a horizontal shift to the right if c is less than 0. In other words, look for minus c. Last, we have d. It is a vertical shift up if d is greater than 0. In other words, look for plus d. It is a vertical shift down if d is less than 0. In other words, look for minus d. Another thing we are going to be working on is taking function notation into equation form. For example, given f of x equals the square root of x, g of x equals negative 4 times f of 2x plus 3 plus 1. We want to be able to take it and write it in equation form. This is called function notation form. So equation form will look like the following. Here we have negative 4 times the square root of 2x plus 3 plus 1. So what exactly changed? Well, what we have is we took this f parentheses component right here. That's all we did. We took that and replaced it with the square root symbol. So everything that was on the inside of the parentheses stays underneath the square root. Everything on the outside of the parentheses, outside of the f, stays exactly where they were. So all we did was just replace the f parentheses with the square root symbol. Let's look at our first example. Given f of x equals the square root of x, g of x equals 1/2 of f times x plus 4 minus 3. First thing we're going to do is we're going to take this function in function notation and rewrite it in equation form. Okay, now that I have the function in equation form, what I want to do is I kind of like to rewrite it so that my minus 3 is not at the end, so it does not get confused with being underneath the radical. So what I'm going to do is I'm going to fix it using my properties of algebra, just so that I have minus 3 at the front. Okay, now it is negative 3 plus 1/2 of the square root of x plus 4. This function is still the same as what we had previously. I just applied the commutative property of addition. So now the next thing I'm going to do is I can see from the function that this minus 3 here means that all of these points shift down 3 units. The 1/2 means that the function is vertically compressed. So I'm squeezing down on the graph. And that the plus 4 on the inside just simply means that we're going to shift the graph to the left 4 units. So how does this look on the graph when we apply this? So the first thing I'm going to do is I'm going to apply the vertical dilation. I'm going to apply that first, and then I'm going to move all the rest of the points based on the translation. Okay, by first applying the vertical dilation, I'm going to compress it by half. Each of these points is half of its height. Well, half of 0 is still 0, half of 1 is half of 2 is 1, and half of 3 is 1.5. The next thing I'm going to do is I'm going to take those points and I'm going to shift them down. I like to do the vertical movements first before I do the horizontal. So I'm going to shift them down 3 units. Okay, all the points have been shifted. What I'm going to do is I'm going to go ahead and finish drawing the rest of this line so you can see what the actual shape of the graph now begins to look like. As you can see, it was a little bit more flat now. Finally, what I'm going to do is I'm going to take the x plus 4 and I'm going to move all the graph to the left 4 units. Okay, so as you can see, we have moved the graph down 3 units, we moved it left 4 units, and we took the graph and squished it down by half the height. There is no reflection, neither A nor B is negative, and then there was also no horizontal dilation either. The x value on the inside was not being affected or being multiplied by anything. Okay, next I'm going to go ahead and take this into Desmos to see if I can produce the same graph using a transformations visualizer that I built for this. All right, so on this tool here, I have f of x equals the square root of x. I have g of x equals the function that I'm trying to use. What I'm going to do is, we don't have to worry about this n equals 9. It's just focusing on this point over here. I do know that I have a vertical translation down 3 units. So I'm going to subtract 3 from the original graph. The red line represents the transformed function. So there's your vertical transformation. I also have a horizontal shift to the left, 4 units. And then I had a vertical compression by half. So I'm going to reduce this down to 0.5. And you can see now from the function, the blue line represented the original parent function. The red line represents the transformation function g of x. Now let's apply this to the S-curves, our cubic and cube root functions. The logic is exactly the same, but our anchor point is the inflection point. In other words, this is where the graph crawls through the origin. Now for this first one, we're going to look at the cubic function, f of x equals x cubed. Our transformation g of x equals negative f of x minus 2. First thing I want to do is take my function notation form and rewrite it so that it's in equation form. Okay, so we have g of x equals negative of x minus 2 cubed. Next, we're going to identify any horizontal transformations. So we have the minus 2 on the inside, which means we have a horizontal shift right 2 units. Next, we're going to look to see if we have any horizontal or vertical dilations. And because we don't have any number multiplying the x on the inside, and we're not multiplying by any number more than 1 on the outside, then we do not have any horizontal or vertical dilations. Then we're going to look for any vertical shifts. We do not have anything plus or minus on the end, or we're not even subtracting something from the very front. So we do not have any vertical translations up or down. Finally, we're going to look for any reflections. We have a reflection on the outside. So the negative on the outside just simply means we have a reflection over the x-axis. Next, we're going to take this into our Desmos tool. Okay, so in Desmos, we have f of x equals x cubed. We knew that we had a horizontal shift to the right 2 units, so let's shift the function to the right 2 units. Then we had a reflection over the x-axis. And this is what the graph would look like. The domain for the cubic function is deceptively unrestricted, so it's all real numbers for x. I described the domain as deceptive because if you look at the graph, it kind of looks like it goes towards a left and a right boundary, but in reality, we could just based on how our screen is set up, we could stretch the graph or zoom in on the area, and we can actually see that this graph extends indefinitely to the left and to the right. The range is also going to be unrestricted from negative infinity to positive infinity. Next, let's take a look at the cube root function. Okay, so given f of x equals the cube root of x, g of x is equal to negative 1.5 times f of x minus 2 minus 3. First things as before, we're going to rewrite the function notation form into an equation form. So we have g of x equals negative 1.5 times the cube root of x minus 2 minus 3. Now I'm going to rewrite it so that minus 3 is at the very front so I do not get it confused with being underneath the radical. So that will look like this. However you choose to write it is completely up to you. It is acceptable to have minus 3 on the end instead. Next, we're going to look for any horizontal transformations or horizontal translations first. So on the inside of the function, we have minus 2 on the inside of the radical expression here. That minus 2 tells us that we have a horizontal shift right 2 units. Next, we're going to look for any vertical or horizontal dilations. I have a I have a vertical dilation of 1.5 and it's a negative. So this is going to tell us that it's going to reflect. So it'll be a dilation or stretch by a factor of 1.5 or 3/2, and it will reflect over the x-axis. Last, we're going to look for any vertical translations. So the minus 3, remember we had minus 3 at the end, we had the minus 3 at the front. We could say that that is a vertical translation or a vertical shift down 3 units. Let's take this over into Desmos to graph the function. So we have the cube root of x. So we knew that we had a horizontal shift to the right by 2 units. So let's shift the graph to the right by 2. There we go. Next, we had a vertical dilation, a stretch. So we were expecting the graph to kind of spool upwards by a factor of 1.5. So let's go with a vertical dilation by 1.5. As you can see the graph now, it is stretching upwards and downwards. Okay. It is also going to reflect over the x-axis. So let's change the factor there. So now it's upside down. And last, it had a vertical shift down 3 units. And there you have it. The domain for the cube root is unrestricted from negative infinity to positive infinity, and the range is from negative infinity to positive infinity as well. Keep in mind, this is just like your cubic function, but this time it is the range that is going to have a deceptive value or a deceptive limitations here. So it'll look like it'll flatten out or, just based on how your screen looks or how you draw your graph. So just be careful with these. As always, thank you for watching. If this helped you make sense of these parent functions, smash that like button and be sure to subscribe to my channel to be notified when new videos are added. Thank you, and I'll see you in the future. Class dismissed.